Hi guys, I just want to share with you a relatively fairly easy way to remember the theorem of Pythagoras in Euclidean geometry. It's quite a troublesome section, I must say. So I was just wondering actually, what would be an easy, a simple, straightforward way to explain this? And you know what? I thought maybe if I show you that this is all around circle geometry, your lives will be quite easy. So as you can see, I've got this. I mean, what we know what the theorem says is that if you've got this big triangle, BCE, right, and you draw a line from the vertex of where the right angle is formed, such that that line is perpendicular to the hypotenuse, then these three triangles, triangle number one being this one here, the smaller one, I'll try and highlight that in yellow, being the smaller one, and triangle number two being this one here, and triangle number three being that one there. All these triangles are congruent. Sorry, not congruent, but similar. And so the question then is why, how? And I want to show you the simplicity of every that comes with drawing circles around this. So I'm going to draw a circle around triangle BCD, if you like. So oops, oh, I messed up my sketch there. Okay, got it back. Triangle BCD, which is this triangle. I've drawn the circle, but I'm going to draw another circle around triangle CDE like that. So watch. So here are my two circles, and I want you to see the beauty that comes with all this. And once you see this and you remember your circle theorems, you will note that we are actually done with the theorem of Pythagoras. So let's bring it to life now. Watch what happens. So I need you to then note, once I've got these two circles, I need you to note that number one, the line CE is actually a tangent to the green circle. So please beware, CE is actually a tangent to the green circle. And how do I know this? Because radius is perpendicular to the tangent. So that's a tangent, that's the radius. Obviously, that O is the center. So it must be a tangent. Another one, I can also conclude that CE is actually a diameter to the pink circle. And how do I know that? Because this angle here is a 90-degree. And so by converse of angle in a semicircle, CE must be a diameter. I just want us to make these obvious facts so that we are together. So it then turns out that CD is a common chord to both circles, right? And then obviously BD are also and DE are also chords and in the respective circles. Now watch this. The angle, this angle here, let's call that angle C1. Let's call this one C2. The angle C1 is actually equal to the angle B by a tan chord. And similarly, the angle C2 is actually equal to angle E by the same principle, tan chord. So then that makes life easy for you, right? Because you can see then that, oh, wait, hang on a second. So this angle is actually equal to that angle, and this angle here is actually equal to that angle. So obviously the other one goes without saying. There's a right angle there. Then you see your similar triangles. What are the similar triangles? Well, let's start with the big one, the main triangle. The triangle, let's call it CBE. CBE is similar to which triangle? Remember, the equal angles are very important. So angle C is my right angle triangle in CBE. So I'll compare that with which triangle do I want to start with? I think I want to start with this one. And then from that one, I will come to that one. So let's start with the red triangle. So if I compare, and I want to show that CBE is similar to the red one, then since I started with a right angle there, I'm going to start with a right angle here, all right? Then I look at B, the angle B in triangle CBE. That angle B, I hope you see it is actually equal to the angle C. This D does not look like a D. So let's write it nicely. It's D. And then that angle there at B is actually equal to the angle at C by tan chord. And then obviously E is common, so we will write E like that because it is indeed common. The way I've written DCE here is really not convincing. It's worrying me. Ah, that's better, I think. So DCE, because I went CBE. Then the last one, the green one. So this must be similar to. What is the similar to? Well, we're going to go for the green triangle. In each case, we've started with a right angle. So I've got to start with the right angle in the green triangle, and that turns out to be angle D. Then, if I look at this previous one here, there's a C, right? And that C in the green triangle is equal to the B. If you like, you may say this B happens to be common to the B in that first triangle. All right, so we're gonna go D, B, and without any further ado, we must end at C because that angle in triangle DBC is equal to the angle EE of triangle CDE. And I thought this should help you actually understand the theorem without having to memorize stuff. Okay, if I give you any two, or rather if I give you the Pythag in any situation, you should be able to derive this. And the beauty of this, of course, this is the power of similarity, right? The beauty of this is that is the following. Watch this now. I can then conclude that CB over DC is equal to BE over CE, which will be equal to CE over DC. Watch. Let's write them down. CB over DC, or if you like, you may actually write it as CD, is equal to BE over CE, and that is the same as CE over DE. In a case where you wanted to prove that something squared is equal to something times something, you will definitely pick that up. And of course, you will say similar triangles. And you can go on and go on. And I mean, another way to do this is to also zoom in and say, okay, if I want stuff that's squared, surely this here with that will give me something squared. And that something squared should be a DC because I see a DC in both. All right. So it's very interesting. And I hope you get to appreciate this, that actually this is how the squares come when you compare these triangles correctly. So let's see now. Let's try and be practical. What happens then if you are just given a right angle triangle and you are required to actually bring this theorem of Pythag into life? Okay, this is the situation that we're going to be presented with. So let's just argue there's a right angle triangle there. So let's come back to this. You just have to draw two circles through the common side. Okay, that's all you have to do. So let's imagine a circle that goes here. That's my first circle. Doesn't have to be perfect. And then let's imagine another circle that goes through this. All right. If you look at the red circle and you look at the green circle, we need to see, at least for a start, diameters. So obviously, let's bring some letters to light. Actually, let's bring letters into the picture. A, B, C, and then D. And I want to have a D1 and a D2 there. And then I'm going to have maybe an A1 and an A2 here. And I think that should be okay, right? Now, AD is our common chord. Surely it is a chord. to both circles, right? We do note that. And then what I want us to do now is to actually get the angles that are the same. The angles that are the same. So I need you to note, if we start with the red circle, maybe let me solidify it. If we start with the red circle, I want you to note that CA is a tangent to the red circle. And because CA is a tangent to the red circle, it means that the angle A2 must be equal to the angle B by tan chord. So that's very important to note. So A2 here must actually be equal to angle B. All right. Then uh, we must have another line which is a tangent to the smaller circle, the green circle. And I'm hoping you capture that. I'm hoping you get which line that is. And of course, that's line BA, because remember, we can conclude that D1 is a right angle. And if D1 is a right angle, then AC becomes a diameter to the green circle. And because red is perpendicular to a tangent, then AB must be a tangent. We have actually even proven that AB is also a tangent to the red circle. Then by tan chord again, it becomes easy then to see that A1 is equal to angle C. Then bravo, look at that. We are done. We can write our similar triangles. So I will start with triangle ABC. And I hope you note that I deliberately choose the right angle first when I look at the main outer triangle ABC. So I start with angle A, then I go to B, then I go to C. Then I can really start choosing any triangle because I know which angles are the same. So if I take, let's bring those numbers again. Let's call this triangle 1 and triangle 2. So if I take triangle 1, for example, then in triangle 1, the right angle there is D1. So I must start at D. Now I said B. The angle that is equal to B in that triangle is angle A2. So I must go for A. And then finally, I would have said BC. I mean, C is obviously a common in both triangles. It is a common angle. Then finally, triangle number 2. I always want to start at a what? At a right angle. So it's a D. Then if I look at the previous one, I said DAC. So the angle which is equal to angle A2 is angle B. So I must say B. And then obviously I must say angle A1, which is obviously equal to C there. So just like that, of course, your reason here will be line from, oh my word, it's a very long one, from a right angle vertex perpendicular to the hypotenuse. Line from right angle vertex perpendicular to the hypotenuse. That's what allows you to say all this. And guess what? Watch this again. It means AB over DA, or AD if you like, should be equal to BC over AC, and that should also be AC over DC. I have just compared the first two thanks to similar triangles. I can compare the first and the last, and that will bring me the following ratios. AB over BD, I'm just writing the letters, the sides in alphabetical order. AB over BD, that is BC over AB, and that should also be AC over AD. Reason is the same, similar triangles. So then let's compare the last two, those. So according to the fact that they are similar triangles, then I can go AD over BD is equal to AC over AB, and this is equal to CD over AD. Again, similar triangles. take note that in each case, you have squares coming up. In this one, we have an AC squared coming up. All right. In this one, we have an AB squared being a result as well. In the last one, you have an AD squared coming out there. So let's write those together. Watch. Here, AC squared is ABC times ADC. In the second scenario, AB squared is actually ABC times ABD. And in the final and third scenario, AD squared is actually ABD. That looks like a 13. Let's try and write it nicely. Is equal to a BD times a CD. So that's how you can easily get your square ratios without having to sort of memorize this. And I like this because it brings your Euclidean geometry very much to life. It brings your circle theorems in particular to life, even the proofs that you easily forget. I mean, look at how we proved here that CE is a diameter by just thinking of the converse of angle in a semicircle. Look at how we could also actually prove that CE is not just a diameter to the pink circle, but it is also a tangent to the green circle by the fact that there's a right angle there. So I hope you really find this helpful. Your understanding of this theorem really should be very easy if you can do this. So go ahead and just randomly draw a right angle triangle, randomly draw a right angle triangle like that. And then, of course, you indicate your right angle. And then you just draw a line from that right angle, where the right angle is formed, and have that line perpendicular to the hypotenuse. Label your triangle M, N, P. Maybe let's have a Q there, and then maybe Q1, Q2, N1, N2, and see if you can bring those three similar triangles. You run out of ideas, try and draw the circle. Remember how we draw our circles through the common side. Basically, that you're going to have two circles going through that. So just try that and practice this. It should make your life really easy when it comes to this theorem. Thanks for tuning in, guys. Cheers.